In this experiment, we're going to explore chemical reactions and see how different chemicals react to produce new substances. All chemical reactions involve chemical change, which is when a substance is converted into one or more new substances that have different chemical formulas and chemical properties. So anytime there is a chemical change, we are changing the chemical formula of a compound. And anytime we change the chemical formula, we are completely changing the identity of the compound. So we're going to start off with a chemical and produce something different throughout the course of the reaction. And any chemical reaction involves chemical change. So there are certain things that you can look for as evidence that a chemical reaction is occurring. If you happen to see a change in color, that is a good indication that some kind of chemical reaction has occurred. Or if you see the formation of a gas, so suppose that you mix two liquids together and you notice bubbling or fizzing, that is indicating that a gas is being produced throughout the course of the reaction. If you notice the formation of a solid, and of course this is if you were to start off with two substances that are not solids. So suppose you mix two liquids together and all of a sudden a solid emerges and crashes out of solution, that solid is what we call a precipitate. And that process is called precipitation. So if a solid emerges when you started off with things that aren't solid, that is indication that a chemical reaction is happening. If heat or a flame were either produced or absorbed, so if you are doing a reaction and all of a sudden your test tube starts to feel really hot or really cold, that is indication that something is happening. So if you are doing a chemical reaction and you're mixing two things together and you're not noticing any of these things, you don't see a change in color, you don't see the formation of a gas or precipitation, then the next thing to look for would be to see if any heat is being produced. So in that scenario, you will want to make sure that you are making contact with your test tube and really trying to feel for any type of temperature change that might be occurring. Okay, so when we do a chemical reaction, we are going to write a chemical equation that indicates what is happening in that reaction. So this would be an example of a chemical equation where we are taking solid carbon, we're reacting it with oxygen gas, and it's producing carbon dioxide gas. And notice how the formulas are changing here. So we're starting off with carbon by itself and oxygen by itself, and then in the end, those get fused together into a new compound, CO2. So everything on the left side of the equation, these are the reactants. So these are things that we are putting into the reaction, and on the right side of the equation, we are forming a product. So reactants will always be on the left, products will always be on the right side of the equation. This little symbol right here, delta, that means heat. So that's telling us this reaction is being heated. You may also notice that there are little symbols after each chemical formula, and these are indicating the physical state of the compound. So the little S means solid. That is telling us we're using solid carbon. L, there's no L in this equation, but you could see that come up. L means liquid. G means gas, so we are using oxygen gas and producing carbon dioxide gas. And sometimes you'll see a little AQ, that means aqueous, and it's saying that this compound is dissolved in water. There are 5 different types of chemical reactions, and we'll explore them. In a combination reaction, 2 or more elements are going to combine to form one product. So if we think of this in terms of just, let's say, variables, if we take compound A and compound B and we combine them together into a new compound, they would form the compound AB. So we took 2 separate substances and we combined them together into one. So one example of that would be if sulfur reacts with oxygen gas to produce sulfur dioxide. So here, sulfur was by itself, oxygen was by itself, and now we fuse them together chemically into one compound. And that's a combination reaction. We start with 2 or more elements and we combine them into a new product. Decomposition is the exact opposite of combination. Here we're starting with one reactant and it's going to split up into two or more products. So here we would be starting with compound AB and it would separate into compound A and then compound B separately. So for example, if we were to take calcium carbonate, here that compound can split apart into calcium oxide and carbon dioxide. So here we're taking one compound and we're splitting it apart into two compounds. So combination and decomposition are opposites of each other. Combustion is a completely separate type of category. In a combustion reaction, we are burning something. So this involves burning a substance. And most of the time, the combustion reactions that you will see involve carbon-containing compounds. So we will have some sort of carbon-containing compound that burns in the presence of oxygen. And we know that if you were to cut off a oxygen supply to a fire, the fire goes out, which means that combustion requires oxygen in order to continue. And of course, one of the products that is formed in combustion is carbon dioxide and water. And of course, some energy is produced because this is an exothermic reaction. So combustions will always have the same format. There will be some kind of hydrocarbon. So we call this a hydrocarbon because it contains carbon and hydrogen. And the only thing that will vary in hydrocarbons is the amount of carbon and the amount of hydrogen. So I tend to write them as variables, Cx and Hy, meaning that the amount of carbon will change, the amount of hydrogen will change. So I write those as variables. So this could really be anything. It could be C2H6, it could be C6H6, it could be C5H12. The amount of carbon and the amount of hydrogen can vary. But in any case, as long as it's a hydrocarbon, this will be one of the reactants for the combustion reaction. So it will always involve a hydrocarbon. Oxygen will always be one of the reactants because oxygen is required for a flame to burn. And the products will always be the same. The products will always be carbon dioxide and water, and that will not change. So everything that I colored here in blue is always going to be the same. You'll always have oxygen, you'll always produce carbon dioxide and water. The only thing that will vary is the identity of the hydrocarbon. So predicting the products of combustions is pretty straightforward. Always carbon dioxide, always water. There are a couple more reactions here. In a single replacement reaction, we're going to take a reacting element and it's going to switch places with another element in the other reacting compound. So we'll always have something that is off by itself, like A here. And then we'll have a compound that it's going to react with. So BC is a compound and A is just an element that is off by itself. And what's going to happen is that A is going to come in and it's going to kick out one of these reactants. So you can see how in the products it displaced B and it formed a compound with C. And now B goes off to be by itself. That is a single replacement reaction, where one reacting element comes in and it displaces something else. And here's an example of that. Here we have zinc, and notice that it's saying that we have solid zinc, which means zinc is in its elemental form. It just exists as a metal off by itself. It is not part of a compound, elemental. And then it reacts with hydrochloric acid or hydrogen chloride. So here we have a compound, right? We have hydrogen and we have chloride that are bonded to each other right now. And then in the product side, we can see that hydrogen went off to be by itself. And here it is expressed as H2 because hydrogen is diatomic in nature. It does not exist as just one hydrogen atom. It's going to form a molecule with another hydrogen atom because that is the more stable form. So hydrogen went off to be by itself. And the other product is zinc bonded to chloride. So it looks like zinc came in and it displaced hydrogen. Hydrogen went off to be its own thing, and zinc formed a compound with chloride. So that is a single replacement reaction. There's also a double replacement. And in a double replacement, it will be very similar, but here we will have two elements that will change places. So the way that we can think about this is that positive ions, which we all know are cations, in reacting compounds are going to switch places. So here we have A bonded to B, and then we have C bonded to D. So we're just going to switch the places of the reactants. So instead of A being bonded to B, we're going to bond it to D. And instead of B being bonded to A, it's going to be bonded to C. And I'm keeping the order here because when we write chemical formulas, by convention, we always write the cation first, which implies that A and C are cations and B and D are anions, which means that when A switches places with something, it has to take up D because that's the only anion that is available. That's why we write AD and not AC instead. So below there is an example of a double replacement reaction, and you can see we have barium that is bonded to chloride. Maybe I should keep my colors consistent here. So barium bonded to chloride, and then we have sodium that is bonded to sulfate. And when we look at the product, we have barium that is now bonded to sulfate, and we have sodium that is bonded to chloride. So you can see how both compounds changed places. If you think of barium as A and chloride as B, and you think of sodium as C and sulfate as D, we now end up with A, D, and with C, and I lost the other one, B. There we go. So you can see how everything changed places, and that is a double replacement reaction. Now, you can explore this in a little bit more detail. What we could do is break down the compounds into the elements that they came from. So if we were to take barium chloride apart, what we could do is uncross the charges. And because there's nothing after barium, then that means that the subscript is 1. So we could give the 1 back to chloride, and we could give the 2 back to barium. Alternatively, we could look at the periodic table and recognize that barium has a charge of +2 and chloride has a charge of -1. We could do the same thing with sodium sulfate. So if we were to look at the periodic table, we know that sodium has a charge of +1, and sulfate is a polyatomic ion with a charge of -2. So these are the compounds or the ions that we are starting with. If we are doing a double replacement reaction, then that means that we have to take a cation and we have to give it a different anion. So here barium was bonded to chloride, and the only other thing I can give it then is sulfate. I can't combine barium with sodium because I can't put two positive charges next to each other. On the other hand, that is going to leave the sodium and the chloride. That's the only other option. So to make the products, we will take these ions and we will write new formulas. Well, if we look at barium and sulfate, the charges are going to cancel out. So that means when we write our formula, we can just write this as BaSO4. And same thing with sodium and chloride. The charges here are going to cancel out, so we could just write this product as NaCl. And that's where our products here come from. We are switching the order of the cations. We could do the same type of thing in the single replacement reaction that we were looking at. So here we are starting off with zinc in its elemental form. And if it's elemental, it means it doesn't have a charge. It is neutral. So you could give it a charge of 0, or you could just leave it the way that it currently is. Hydrogen chloride, well, that is a compound. And if we look at the periodic table, we know that chloride has a charge of -1. Hydrogen would have a charge of +1. So that is what is currently bonded to each other. Now, in the product side, if we did not know what the products were and had to predict them, well, we would need to recognize that we need to form a compound. So the only anion that we have is chloride. And since right now it's bonded to hydrogen, well, I can't bond it to hydrogen again, or I'll end up with the same reactant that I started with. So the only option would be for it to bond to zinc. And of course, it can't bond to zinc if zinc is neutral, because it doesn't have a charge right now. So what will have to happen is zinc is going to have to form an ion. And when zinc becomes a cation, it has a charge of +2. So zinc is one of the exceptions of transition metals. It always has a charge of +2. That one is, in fact, predictable. So when it forms a cation, well, now we can use it to form a compound. So the chloride will be bonded to zinc. And when we write a new chemical formula, we are just going to cross the charges over. And of course, if the charge is 1, then, or if the subscript is 1, we don't have to include it. So that formula would be ZnCl2. Now, of course, this leaves hydrogen by itself. And we know that in nature, hydrogen is diatomic. So this is going to have to be H2 gas. And that's where these products come from. There's one more reaction type that we have not yet discussed, and that is oxidation-reduction, which we also call redox reactions. This is actually a broader umbrella term that encompasses lots of different types of reactions. So single replacement is also a redox reaction. Combustion is also a redox reaction. So this is a broader category that has different reaction types within it. In a redox reaction, an electron is going to be transferred from one substance to another. So for example, here we have A, and then we have B, and there is an electron that is currently on A. So in a redox reaction, that electron is going to be transferred from one substance to another. So instead of having that electron attached to A, we are going to give it to B instead. And in a nutshell, that is a redox reaction. All we did was transfer that electron. When that happens, we say that the substance that lost the electron got oxidized. And here, A lost electrons, so A is the one that got oxidized. The substance that gained an electron got reduced. So since B gained the electron, we say that B got reduced. And there's a mnemonic that we can use to remember that. And there are two different ones that you can use. It's completely up to you which one you prefer. So the first one is oil rig. And that is saying that oxidation is loss of electrons and reduction is gain of electrons. The other one is Leo the Lion Goes Grr, that says loss of electrons is oxidation, gain of electrons is reduction. Completely up to you which one you prefer to use, but as long as you get to the answer. Okay, there are few different examples of redox reactions in real life. One of them is iron rusting. So iron rusting is an example of an oxidation reaction when the surface of iron is exposed to oxygen and it forms an oxidation product. Silver tarnishing. So when silver develops a black coating over time, that is an example of oxidation. Or when chips turn stale, if they are exposed to oxygen for a long period of time, that is an example of oxidation. A common type of problem in redox reactions will ask you to identify which substance got oxidized and which substance got reduced. So in those scenarios, it's helpful to separate them into two different equations. For now, you can ignore the coefficients that are listed in front of all of these reactions or in front of these reactants or products. These are telling us how much of each one we have, and that comes from balancing reactions, which we will cover in a different video. But for now, I'm going to look at each of these substances individually. And right now we have iron in its solid form. So that means this is iron in its normal elemental form, which means right now iron has a charge of 0. It is neutral because it's in its elemental form. And on the right side of the equation, I'm going to take a look at that compound and I'm going to break it down into the ions that it came from. We know by looking at the periodic table that oxygen or oxide has a charge of -2. Iron, then, we can figure out the charge on that based off of the charge from the oxide. And if we were to uncross the charges in this formula, we could give the 3 back to iron, the 2 back to oxide, and that would give us a charge of -2 on oxide and a charge of +3 on iron. And that makes sense. If we look at the periodic table, we know that the charge on oxide is -2, so uncrossing works just fine here. And that means that the charge on iron is +3 on the product side. So what's happening here is that on the left side of the equation, on the reactant side, we are starting with neutral iron, no charge, and on the product end, we end up with iron with a charge of +3. So to end up with a charge of +3, that means that iron lost electrons. In fact, it lost 3 electrons. And if it lost electrons, if we look back at our mnemonic oil rig, oxidation is loss of electrons. So that means that iron got oxidized. We can do the exact same thing with oxygen. So on the left side of the equation, on the reactant side, we are starting with O2 in the gas form. Now we know that oxygen is one of the diatomic molecules. So in nature, oxygen appears as O2. That is telling us that this is currently in its elemental form, which means it does not have a charge. It is neutral. On the product side, we end up with oxide with a -2 charge. Well, in order to end up with a -2 charge, it means it gained electrons. So oxygen gained electrons, and since it gained electrons, it means oxygen got reduced. So that is how you can handle that type of problem and identify what is being oxidized, what is being reduced. Let's try one more. So in this example, we have solid zinc that is reacting with copper chloride in its aqueous form. This just means that this is dissolved in water. It is currently in solution. And that is forming zinc chloride and solid copper. So pause this video, take a moment, try to identify what is being oxidized and what is being reduced. All right. The first thing I'm going to do is break apart the compounds into the ions that they came from. So here we have copper with a +2 charge. And the way I'm getting that is by looking at that subscript and giving that back to copper. And chloride, of course, based off the periodic table, has a charge of -1. And that makes sense because there should be a subscript here of 1. But if the subscript is 1, we don't bother to write that in. On the right side of the equation, we have zinc chloride. Same sort of thing here. I will give the 2 back to zinc. So the charge on zinc is +2, and the charge on chloride is -1. Notice that going from the left to the right side of the equation, nothing changes with chloride, which means that chloride isn't actually doing anything. So what we could do is just ignore it. We'll say we'll leave chloride alone. It's not really involved in the reaction. It's not changing at all. What is changing is the zinc and the copper. On the left side of the equation, we are starting off with zinc in its elemental form. So I'm going to write a separate equation for what happens to zinc and another one for what happens to copper. So for zinc, on the reactant side, we have zinc in its elemental form, solid zinc. That means it has a charge of 0 because it's neutral. On the right side of the equation, on the product side, we end up with zinc with a +2 charge. Well, in order to become a cation, it means it must have lost 2 electrons. So zinc lost electrons, which means zinc got oxidized. Well, by order of elimination, we know that copper must have been reduced then, but we can take a look at that individually. On the reactant side, we are starting off with copper with a +2 charge. And on the product side, we are ending up with elemental copper. So solid copper, which means it's in its elemental form, which means it doesn't have a charge. It has a charge of 0. So in order to go from a cation into a neutral ion, well, it means that copper must have gained electrons. And since it gained electrons, it means it got reduced. And that is it. That is how you do that type of problem.